So since now we have a very clear idea about how publisher publishes the message to Exchange, and then Exchange routes that message to the dedicated queues, and then how consumer consumes those messages from these queues. Now it's very clear. Now to understand every point of failure, what we will do is, instead of going from there to here, we will move from here to there in the backward direction and cover every point of failure here and how to handle that thing. So if we talk about this consumer, suppose let's say it has made the connection with the broker successfully. After making a connection, it has also obtained the channel, and then after it has made the channel also, then it has basically created the queue and bind that queue to the Exchange. Suppose this is the queue which it's listening to, and this queue has some binding and this is basically a topic exchange, because topic exchange is the most commonly used exchange. Okay, but you can use any kind of exchange. Okay, and this binding has a routing key. Now suppose let's say publisher publishes a message and it has routed that message, this exchange has routed that message to this queue. This is a Q2, and this Q2, this consumer is listening to that queue. Now this message comes here, this message is pushed to the consumer. Now what can happen is, suppose let's say this message has been pushed to this consumer and this queue has removed this message from queue. Now it's possible that this message has been pushed by this queue, but this consumer server is down right now. It's possible that this consumer server crashes and this is down, or it's possible that this packet is lost due to some network issues. Although it will be using a TCP protocol here, but it's possible that TCP connection is broken and we have lost the packet. So how do we handle that case? What we can do is we can use the mechanism of acknowledgements. And acknowledgements were being used in TCP connection also, that we discussed earlier, but here also at AMQP level we will also use acknowledgements, and this will not be synchronous. Like suppose let's say it's possible that Q2 pushes the message and then consumer will send an acknowledgement after it has processed the message, but it's possible that this queue, like instead of waiting for this acknowledgement and then pushing another message to other, suppose let's say there are other consumer also which is listening to this queue, so it's possible that it has messages ready but it is waiting for the acknowledgement to come, only then it will, and then this queue pushes that message to this consumer or this consumer. So that will be a kind of synchronous operation. But generally what happens is, generally how this RabbitMQ handles is, instead of waiting for this acknowledgement, it handles this thing asynchronously to make it fast. But now this acknowledgement can be done in two ways. One is auto acknowledgement and then it's manual acknowledgement. First let's talk about this auto acknowledgement. So what happens is, by default, suppose let's say this message comes here and this message is pushed. So this queue will not wait for acknowledgement from this consumer. This message will automatically be acknowledged and removed from the queue. This is a normal flow. But in this case, it's possible that we might lose this packet due to network loss, or if the consumer is down, then also it is possible, right? Or also it's possible that this consumer receives that message and after receiving, it crashes before processing it. Alright, so various cases are possible here where it can fail. Suppose let's say this message comes here, consumer performs that task and do some DB operation or some cache operation or something which do some alteration here. So it's possible that this publisher is checking that DB and getting those records which were in previous state. So if that doesn't happen, it is sending those tasks, those messages again and again. So if it's a kind of a repetitive task, then this works fine. Like you can auto acknowledge it, because of course if it's dropped here, then the next time when the publisher will see, okay, I have to send this record, it will again send that same record, the same message it will be sent. So that is fine totally. But if this publisher is not sending that message in repetitive fashion, that message is very important, we can't even lose this message. Suppose let's say this publisher is not even repetitive, but that message is not very important, we can some loss or some packet loss is fine. then this thing is totally works, because it's fast also, right? Because queue will not have to wait. It will directly acknowledge and remove that message. So it's very fast and very good actually. But now, suppose let's say this publisher publishes a message only once, and publisher has to make sure that it is being executed by this consumer. Some operations have been performed on that, and you have to make sure pakka that message is execute that this consumer consumes that message and perform operations on that. In those critical situations, what you can do is you can use this manual acknowledgement. So what this manual acknowledgement means is this queue will push the message, okay, and then of course, since we are using a TCP connection, it will receive the acknowledgements at TCP level. That will be immediate only, but this doesn't mean that consumer has performed operations on that, right? Because that is a normal acknowledgements at TCP level. But what we want is, we want this consumer to consume that message and perform all the operations and then send the acknowledgement. So that will be done at AMQP level. So what this consumer will do is, this will consume that message, perform the operations, and then send the acknowledgement to this queue. And then this queue will remove that message from the queue after receiving the acknowledgement from the consumer. So in this way, if we use this manual acknowledgement, we can be sure that this message is consumed by the consumer and all the operations have been performed. But here also one edge case is there. What if this message is consumed? Okay, cool. So what this acknowledgement will assure is, suppose let's say this message is sent here, but it fails due to certain reasons. If it has not received acknowledgement at TCP level, then of course TCP will do some retries to send the packet and make sure that it receives to consumer, okay. And after certain retries also it will stop, right? Like suppose TCP performs some 5 retries for this packet to be sent to this consumer, and after that maybe that connection is broken or something. So we can't depend on TCP here completely. But and also suppose let's say this queue pushes that message, it is received by the consumer, and then this consumer fails or it's not available. So this queue will not receive this acknowledgement. So it will wait for certain duration, and if it has not received this acknowledgement, it will again push that message to this consumer. So that will work here, right? But what if, suppose let's say this queue pushes that message, consumer performs certain operations, what actually has to be done, and then after performing those operations, it crashes before sending the acknowledgement. Now, if queue wait for this acknowledgement, and in this case, it will not receive any acknowledgement because this consumer is crashed, right? And this acknowledgement is like some in-memory operation, so consumer will never know again that I have to send the acknowledgement again, right? So because once the consumer restarts, all the in-memory is deleted by default. So in this case also, this queue will try to push that message again, but consumer has already performed those operations on DB or at cache level or some other operations that it has to perform. So what you have to do is you have to make sure that even in case of repetition, in case of manual acknowledgement, you have to make system in such a way, you have to write the code in such a way that it is able to handle those repetitive cases. It should not lead to data inconsistency or any kind of data redundancy, okay. So here that you have to make sure. So suppose let's say if you are performing some DB operations, what you can do is, suppose let's say some message comes and you are modifying certain like one row of DB, you're modifying that. So suppose let's say its state, if its earlier was pending, it's changed to save state. Now in case that message comes again, it will see that message is already saved, so it will not do anything. So here you can actually handle that thing. But now there is one more edge case here. Suppose let's say this consumer consumes that message, and right now this consumer load the load on this consumer is very high. So this consumer has not failed actually. It has consumed the event and it's still processing this task. Okay, it's still executing this task to be done on DB. So it's in middle here. But the duration for which this queue will wait for this acknowledgement has already crossed. Suppose let's say it waits for 5 minutes and consumer has not completed this task even within 5 minutes. So here it's 6 minutes. So this queue will see that acknowledgement has not been received. It will again pushes that message. So here consumer is already doing the operation here. So what you can do is you can use DB logs here. You can log this row in case message is again received. This consumer will again try to update the same record, but since the earlier operation has already lock on this row, it will not be able to do so. It will give error. So in this case, you will actually handle that thing. And for this, of course, it will not send the acknowledgement, right? The second time it pushes the message, for this time also it will not send the acknowledgement. So this may happen for certain duration till this completes or fails. Suppose let's say it completes. It completes later on, some later stage. So what will happen is this queue will send again, but this consumer will see that it has already been saved state, so it will send the acknowledgement. That is fine. But what if it fails? At some later stage, it fails. If it fails, what will happen is this queue will push the message again to the consumer. This consumer will again log the row, and this time it can log the row because now it has failed. So now there is no lock on this row, right? So this consumer can again apply the lock over this row, fetch that record and update the state here and then send the acknowledgement. So in this case, we have made sure in case of manual acknowledgement, there is no chance of data inconsistency. And this is called as idempotency. Idempotency is nothing but how many times we send the same thing, this consumer will be able to handle that thing. Okay, so that is something called as idempotency. So now we have made sure how to handle any edge case possible between these two things. Like if message is pushed to the consumer, it will go to consumer pakka. Alright. And this TCP acknowledgement will be sent because here we don't have a control, right? This acknowledgement was sent later on asynchronously, but this TCP acknowledgement is sent immediately as soon as it has sent the message. Before consumer process that message also, the acknowledgement is sent at that time itself because it is something at transport layer. This will not wait till this consumer performs something or not. It will just say I have that the message that you are trying to send to this consumer, it has already been sent, all packets it has received. Now I am sending the acknowledgement that all messages have been received here. So that is the role of TCP. But due to but TCP can fail, like message can drop here in case TCP connection is lost. So we have understood how many edge cases were there, right? There were like TCP connection packet drop because of TCP connection loss. Even if the packet is received by consumer, then also it's possible that this consumer is not available. If consumer is not available in starting itself, then TCP will make some retries, but after certain duration, after certain retries, the connection will be broken. So that edge case we have also covered. And then it's possible that consumer is available in starting, so TCP acknowledgement will be sent here, but then consumer fails to process that, it crashes before processing. Then we also handle the case when consumer consumes the task and after processing that task, it crashes but fails to send the acknowledgement. And also it's possible that because of this TCP connection loss, like the TCP connection between these two is lost. So we have covered a lot of edge cases here. But now one more edge case is there. Suppose let's say this consumer consumes that task, performs everything, then sends the acknowledgement. But what if this server is down? The server is down at that point of time. like before it receives the acknowledgement, the server crashes. Then of course, since we are using TCP, the TCP connection will be broken, and this message will be lost completely. So the main goal of TCP connection is that till the connection is maintained, till that point of time it assures reliability. But in any case the TCP connection is broken, then all the things will be lost. Then it's your responsibility to handle that case. So in that case, what we can use is, we can use some feature of RabbitMQ, because RabbitMQ is working at application layer. So now RabbitMQ provides one more feature, that is durable queues. So what will happen is durable queues and persistent messages. Persistent message. What these two features combine provide is, suppose let's say this consumer sends the acknowledgement, but this acknowledgement fails due to some reasons. This consumer may or may not know that this acknowledgement has been received by this queue or not, because if it's a TCP connection loss, then this consumer might know that this acknowledgement was not sent again. But then also it can't do anything, right? It can't do anything here. And also it's possible that this acknowledgement is sent successfully. After it has consumed that acknowledgement, before removing that message, this queue drops, like this queue, this server crashes. So there are two possible cases here, but in both cases this consumer can't do anything. So what this thing will help is these two features. When we will restart this broker again, what will happen is, since we were using durable queue, since this Q2 was durable, and we will specify this durability of queue while creating the queue. So we can pass some extra parameters at the time when we have created this queue. So we will have to make this queue durable, and when we are publishing that message to the exchange, it's publisher responsibility to mark that message as persistent. Okay, so if we have used these two features, what will happen is the server restarts again. So this message will be stored in disk. This server will be having a disk, like a hard disk or some permanent memory, which will permanently hold the memory even in case of shutdown, server shutdown. So when it will restart, it will see that acknowledgement has not been received. So it will again push that message to the queue, to the consumer, and consumer has already processed that message earlier. So it's fine because our consumer was idempotent. So then also it will see that our state was saved only. So it will not do anything. It will just send the acknowledgement. So this is how we can actually ensure full reliability in case of this part. Alright, whether it's a server crash, network drop, packet loss, or TCP connection, if the TCP connection is broken, or anything. Right? So this part is done. And also one more thing that I forgot here to tell you about is, this acknowledgement can be done in bulk also. Bulk acknowledgements. So instead of acknowledging one message, instead of acknowledging only one message, what you can do is, you can also do a bulk acknowledgement itself. Like suppose this consumer consumes certain messages like 1, 2, 3, 4 and then acknowledge in a single go. So what happens basically is, when this queue pushes the message to this consumer, to each push to the consumer, it allocates the message a delivery tag, and this delivery tag is unique on the channel level. So if one channel has received the message, then it will have a unique delivery tag. So suppose let's say it has consumed the messages with delivery tag as 1, 2, 3, 4. So what this consumer can do is, instead of acknowledging them one by one, because that will of course increase the load, more network calls will be made. Instead of that, what it can do is, it can process all the messages and then acknowledge directly as 4. So if you pass certain parameters here, that some bulk parameter, and you will pass that I am acknowledging this message with 4 delivery tag, So what this queue will assume that it is acknowledging the messages till 4. So all the messages that were sent earlier will be acknowledged as well. So this is called as bulk acknowledgement, and you can do this bulk acknowledgement in form of batches, like batch of 4, batch of 6 or batch of 8 accordingly. So in case this acknowledgement fails, then all the 4 messages will be pushed again. The same batch will be pushed again. So this is something, and your consumer will be able to handle that because of idempotency. So this is called as bulk acknowledgement. Also, one more thing is there, that is prefetch count and prefetch size. Now these two properties work side by side. What happens is, in case you are using this manual acknowledgement, what this consumer can do is, like, queue will push the message one by one normally. But in case of manual acknowledgement, if you have specified this prefetch count as 1, then it will consume only one message in a single time. But if you have specified this prefetch count as 4, so in a single go, the 4 messages can be consumed by this consumer, and it can process those messages side by side, or whatever code you have written here. Okay, so 4 messages will be consumed, and suppose, let's say, it has acknowledged one of the messages here. So 3 messages are now not acknowledged right now. So this consumer can again ask for one more message, so that it can make 4 non-acknowledged messages here. So at a single point of time, there will be at max 4 non-acknowledged message inside the consumer. So that is held by this prefetch count. Or what you can do is, you can specify the prefetch size. What this prefetch size will do is, if you specify certain size here, this consumer will not consume any message if it's crossing this prefetch size. So in case the prefetch size is mentioned here, suppose, let's say, it has consumed 3 messages earlier. So even though prefetch count was 4, right, or if we have not specified anything in prefetch count, that means that it can consume any number of messages it wants. Okay, there is no limit. So in that case, then this prefetch size will work, and this will say that this message can't be consumed by this consumer because it is crossing the size of total messages that are not acknowledged. So that is controlled by this prefetch size attribute. So now we have talked about auto acknowledgement, manual acknowledgement, and this prefetch count and prefetch size. All right. Also, it's possible that instead of acknowledging the message, it will reject the message. Okay, it's also possible that this consumer, instead of acknowledging the message, it is saying that I am not going to process this message, and it will say reject. So for rejecting the message also, there are 2 options. One is NACK, like non-acknowledgement, and another is reject. But both are different. So what this reject is, reject can only reject a message only once at a time. Okay, only one message at a time. So it will reject the message one by one. But this NACK can do the rejection of messages in bulk. Like we were doing the acknowledgement in bulk, this NACK was introduced so that we can reject the messages in bulk. So bulk is available here. Now this reject means that if the consumer rejects this message, and this consumer and this queue successfully receives that rejection, right, what it can do is, this queue can either requeue it, right, it can requeue the message, but this time it will try to send that message to a different consumer instead of this one, because this consumer has already rejected that. But in case you have already only one consumer listening to the queue, that requeuing will happen again and again, and it will again send the message. This consumer will reject that again, then it will again be requeued. So this will become an infinite loop. So you will have to handle that case. So you can either requeue it, or you can discard that message. You can remove that message from the queue completely, or you can route that message to alternate exchange. So here comes the use of alternate exchange. So you will have one more exchange if you have set up. This is alternate exchange. This queue will push that message to this alternate exchange, and it will be taken care by this alternate exchange. And to this alternate exchange also there can be certain queues to which you can set up a consumer, right? This also you can do that. And here also you can assure the reliability by setting up the acknowledgements here. Now we have covered this part completely. Now before we cover this part, let's try to make sure the reliability at this point of time. Okay, so what happens generally is this publisher makes a connection with broker, and then make a channel, and then start publishing the messages through the channel to this exchange. So suppose let's say this publisher sends the message to the exchange, but it's possible that this exchange is not available or the server is down. The server is down right now, so the connection will be broken, the TCP connection will be broken, and that message might lost. Okay, that message might get lost, right? Also it's possible that this exchange takes that message. Okay, it takes that message, but what will happen is this message will be routed to the queue, but it's possible that before it is actually saved to hard disk, like because we were using durable queues and persistent message, before it gets saved to hard disk, the server crashes. So then also a message will be dropped, right? Because TCP connection will send the acknowledgement before itself once this broker has received that, but we have nothing to assure that it has been saved to the disk. So relying on TCP connection is not here, will not work here. And in case this whole server is not there, it is crashed, then this publisher will know that my message is not sent successfully, but it can't do anything right now, because it will try, the TCP will try to retry certain times, but after that time also, if this thing is not available, that message will be lost. Even the publisher knows about that it has not been sent successfully, but it's possible, right? So for handling that case, what we will do is we will use something called as publisher confirms. Now what is this is this thing works on the same principle as we were using here. We were using the acknowledgements here, right? So we will try to use the same kind of acknowledgements here itself. So RabbitMQ, what they did was they established this type of acknowledgement mechanism here also and named it as publisher confirms. So what will happen is this publisher pushes the message to the exchange, and in case message is not persistent and this queue is not durable, so in any either one of this is not present or both are not present, in that case the acknowledgement will be sent basically when this exchange has successfully routed that message to the dedicated queues. Like suppose let's say this message was sent and it has some routing key, and this routing key satisfied the binding keys of these two queues. So once it is routed to these queues successfully, then the acknowledgement will be sent by this exchange. Alright, that is possible. But here also it's possible that we might lose the packets because of server crash of RabbitMQ. So in order to ensure that, we will have to use again durable queues and persistent message. We will use that here, both the things. So once the message is routed to the queues, and once the queue save that message to the disk, only then the acknowledgement will be sent to the publisher. So publisher can do this in case in synchronous fashion also synchronously. Basically this publisher can set up this publisher confirm completely synchronously, like sending one message, waiting for acknowledgement. But this will reduce the throughput by 250 factor. So it will be very slow. If you don't want that, you can do that using batches. You can push like 4 or 5 messages, and then this exchange will send the acknowledgement of those 4 or 5 messages in a single go. That is also possible. One more thing is completely asynchronously. In this case, what will happen is this publisher will send the message, and then it will not wait for the acknowledgement. It will keep on sending. Once the message has been saved to the disk, then this exchange will send the acknowledgement. And here also same delivery tag will also work. in order to acknowledge the message. And this delivery tag, basically this publisher will keep a track of. So basically what will happen is, as soon as the publisher publishes a message, it will store something in memory to keep a track of. It will make a key value pair, like a map, basically map data structure, which is a key and value. So the key will be the delivery tag or the sequence ID. So what it can do is, before the publisher publishes the message, it can first get the sequence ID from this exchange. There's a function in the client library which you can use to get the next sequence ID. So publisher will use that sequence ID and store it in a map, and corresponding to that it will store the message what it is sending. So once the exchange acknowledges that message with the same sequence ID or delivery tag, it will remove this key value from this map. It will remove this thing. So in this way, publisher can keep a track of all the messages that it has sent to the exchange in a kind of a map data structure. So now we are using this acknowledgements here. But now again, it's possible that this acknowledgement has been sent by the exchange, but this acknowledgement is due to some connection drop, this acknowledgement is lost. So in that case also, this publisher, what it will do is, it will again push the same message. So it will lead to redundancy, but since you have made your consumer idempotent, your consumer will be able to handle that case. So that is fine here. Also, it's possible that here, when this exchange is routing the messages to the queues, it's possible that the message routing key, corresponding to this routing key, there are no queues available here. There is no queue binding routing key which satisfies this routing key. So in this case, the message is unroutable. Message cannot be routed to any available queues. So in that case, what can you do is, you can set up an alternate exchange. So here also alternate exchange can actually help us. If message is not routable, you can push this to alternate exchange. And then we have a queue setup here and consumer here. And you can listen to these messages and raise some alert or something if that thing happens. That is how we can actually handle this thing. Also, one more edge case is possible here. Suppose, let's say this acknowledgement is sent, and now, like earlier we have handled a case in case this connection drops. But what if this publisher crashes? Like this exchange has sent the acknowledgement, but this publisher crashes. So in that case, what we can do is, since you are maintaining this map, right, you can store this map in cache, or maybe in DB, or maybe in hard disk, so that even this publisher restarts, right, this thing you have already there. So it will say that if it's present in map, you can again push those messages to exchange. So this is how you can control full reliability from publisher to exchange as well. So in case if anything happens here, like before this message is actually saved to hard disk and the system crashes or something, then your publisher confirm will be able to handle this case, because the acknowledgement will not be received here, and this publisher can actually resend that message again. And it's also possible that you have not set up this alternate exchange. Okay, this alternate exchange is not there. So in case any message is unroutable, in case of any unroutable message, what you can do is, you can set up you can basically return this message back to the publisher. Okay, in case message is unroutable and you have not even set up this alternate exchange, what you can do is, you can set up you can basically send this message again back to the publisher. So you will have to basically ensure that this unroutable message is handled by this publisher. So you will have to basically create one more function here, that is handle unroutable message, so that if in case any unroutable message comes back, then it will be able to handle that. So of course, like if this exchange finds out that this message is unroutable, so it will also send this acknowledgement, and this acknowledgement can be received either before this message is received by the publisher or after that. So you can handle this case in any of the method here, like you can basically requeue that message again to the exchange, or you can discard it, or anything you want to do at publisher level. And in case message is persistent and there is no alternate exchange, what will happen is, this message will be returned first and then the acknowledgement will be sent. Even though if we lose both of the things, like acknowledgement also and this message that has been received, in case of anything, this publisher will know, right? Because it will be in map here. So publisher will again try to repush it again. And the same things will keep on happening again till publisher is finally sure that this message is handled. So nothing to worry about here. So I think we have covered each and every edge case possible here while setting up the RabbitMQ. And with this thing, with all this structure, you can actually ensure that your system is fully reliable. Okay. Other things that are left that you can easily understand by going through the documentation of RabbitMQ. So I have attached everything in the document that I have attached in the description box of this video. You can check that document and you will find every resource possible regarding RabbitMQ in that thing. So what I felt was this thing and understanding AMQP, the basics of AMQP, that was important to teach you in this video, because in video it's actually easy for you to consume the knowledge. Other things I think you can easily understand by going through the documentation and according to your use cases. So I think with this knowledge you will be able to do everything possible. Now if I talk about coding, I think I might create video on how to create a producer and consumer, but I can't create video on every language, so you will have to explore that thing by your own. Like if you are using Java, Python or maybe some other programming language, you will have to install client library according to that language. So all those things are actually available in documentation. They have specified the client library, official client library for every language. So you can check their documentation and use the functions provided there. But the concept will be same here, what I have specified, what I have explained here. So every concept will be same. You will have to relate with your use case and handle the conditions yourself. In case you have any other doubts, you are free to ask me anywhere on any social media. You can basically join our Telegram channel and Discord channel as well. I try to resolve the queries as soon as possible. So I think that's it for this video. If you like this video, do hit the like button and do subscribe to my channel for this kind of videos. And if you really want to basically upgrade your skills, because I generally do not create a basic level videos, I try to take the concept from basics to advanced. So in case you are interested, feel free to subscribe to my channel. It's free. I think that's it, and see you next time.